A note about pH and pKa. pH represents the negative log concentration of H+. This is the mole per liter of hydronium ions in solution. pKa represents the strength of an acid and its ability to dissociate into ions. In aqueous solution, when the concentration of acid and its conjugate base are equal, then the pKa is equal to the pH. Let's take a look at an example of this. For the following acid ionization reaction that is also called an acid dissociation reaction, carbonic acid in water ionizes to its hydronium ion and its conjugate base, hydrogen carbonate. The equilibrium expression is written with the concentration of products divided by the concentration of the reactants. Take the negative log of the left and the right side of the equation gives an equation that can be changed to the pKa is equal to negative log Ka and the pH is equal to the negative log concentration hydronium ion. The last term is 0 for log 1, and this occurs when the concentration of acid and its conjugate base are equal. This is a question on using pH to calculate Ka. Weak acids are in equilibrium with its conjugate base and the hydronium ion. Experimentally, by measuring the pH of a certain concentration of weak acid, we can determine its Ka. For example, a 0.10 molar solution of formic acid gave a pH of 2.38 at 25 degrees Celsius. Calculate Ka. Steps to do this. Write the balanced chemical equation of formic acid in water. Write the equilibrium expression for formic acid. Set up a table called ICE, Initial Change Equilibrium. The pH is the equilibrium concentration of H+. Here is the solution to the question for a 0.10 mole per liter solution of formic acid that gave a pH of 2.38 at 25 degrees Celsius. Calculate Ka. Step 1. Formic acid has only one acidic proton given in red. Step 2. The equilibrium expression is Ka is equal to the product concentrations divided by the concentration of the reactant. Water is omitted because it is the solvent and a liquid. Step 3. Set up the ICE table. This table is the typical setup. With the initial concentration of formic acid is 0.10 moles per liter, and the products have 0 initial concentration. In water, a small amount of acid dissociates, and this is represented by -x in the row under the change. Notice that the water has a line throughout its column because it is omitted. The change in products is represented by +x because this is a 1:1:1 stoichiometry between reactants and products. The equilibrium concentration is then given as the initial and change. For the reactant, formic acid is 0.10 minus x, and for the products, they are each plus x. Step 4. Let's figure out how to enter the proper numbers. The equilibrium concentration of hydronium ion is obtained from the pH. We are given that the pH is equal to 2.38, so the concentration of H+, the hydronium ion, is 10 to the power of minus 2.38. This gives the concentration of H+ as 0.00417 mole per liter. The concentration of HCOO-, the formate ion, which is the conjugate base of the acid, is also the same because the stoichiometry is 1:1. The concentration of formic acid at equilibrium is 0.10 minus 0.0417 moles per liter, which is small and rounding will still give 0.10 mole per liter. The Ka is then determined by substituting the equilibrium concentration into the equilibrium expression, and the Ka turns out to be equal to 1.7 times 10 to the minus 4. In this question, let's look at using Ka to calculate pH, the reverse of the last question. A 0.115 mole per liter solution of hypochlorous acid has a Ka equal to 3.0 times 10 to the minus 8 at 25 degrees Celsius. Calculate the pH. Step 1. Give the balanced chemical equation for the acid ionization water. Step 2. Give the equilibrium expression. Step 3. Set up the ice table. In this ice table, enter the data that you know. We know that the initial amount of acid is 0.115 mole per liter, and the product amounts are 0. We know that a small change in the acid occurs, and this is represented by minus x. Then the products will change both by plus x because the stoichiometry is 1 to 1 to 1. The equilibrium concentration is that now for the acid reactants is 0.115 minus x. This gives the equilibrium amount of the products as x each. It is assumed that the value of x is very small so that 0.115 minus x gives 0.115 mole per liter. We need to solve for x to determine the concentration of H+. To do this, we can substitute these equilibrium variables into the equilibrium expression for Ka of hypochlorous acid, HClO. The formula becomes Ka is equal to x squared divided by 0.115. Is x squared because the concentration of the hydronium ion is times the concentration of the hypochlorite ion, the base. Solving for x requires the square root of both sides. X is then equal to 5.87 times 10 to the power of minus 5. The pH is the negative log 5.87 times 10 to the power of minus 5, and this is 4.23. Determining the percent ionization. The formula for percent ionization is percent ionization is equal to the concentration of H+ at equilibrium over the initial concentration of the acid times 100. For a 0.115 mole per liter solution of hypochlorous acid, it has a Ka equal to 3.0 times 10 to the power of negative 8 at 25 degrees Celsius. The initial concentration of HClO acid was 0.115 mole per liter. At equilibrium, the concentration of H+ is equal to concentration of the ClO minus is equal to 5.87 times 10 to the power of minus 5 mole per liter. So the percent ionization for hypochlorous acid is equal to 5.87 times 10 to the power of negative 5 divided by 0.115 times 100. This is equal to 0.0510%. This means that very little of the hypochlorous acid is ionized, and hypochlorous acid is a weak acid. Acids and bases. Polyprotic acids. Polyprotic acids are acids with more than one proton to donate, more than one to ionize. Proton donation occurs in steps. The first hydrogen must be removed before the second one can. For example, sulfurous acid donates a proton to the water as a base to give the hydronium ion and hydrogen sulfite ion. The Ka is represented by Ka1 is equal to 1.7 times 10 to the minus 2. It is easy to donate the first proton. The second proton comes from hydrogen sulfite ion. It donates a proton to water to produce the hydronium ion and the sulfite ion. Ka2 is equal to 6.4 times 10 to the minus 8, and it gets harder to donate. Sulfurous acid is a weak diprotic acid.